Det var inte mitt val att dra ner.
Nej, det var...
Jag tyckte du kunde ligga kvar.
Jag var inte...
So has everyone been able to do okay with the drop-down menu working on your machine?
What?
The last assignment question, for example, right? You're supposed to copy-paste some functions, and then when you run it, there's a little drop-down menu that comes out with 2 options, and you have to kind of toggle.
You mean change the seed and the seeds?
Yeah, yeah. So, yeah, exactly.
Is that the toggle down?
Yeah, like you can see, you know, when you press that button, you can see lambda equals some value, and then you can choose. Okay.
Yeah, you can change the seed from 0 to 123 or something like that. Yeah.
Okay, because someone suddenly their system, this is not working. But all I'm asking there is something very simple, right? If you have exponential waiting time for the bus arrivals, and if I change the scale, the lambda parameter, what's going to happen? I mean, in that picture, right, where people are waiting and...
if you have the high number, you get more people. If you have the low, or are you talking about lambda?
No, I'm talking about lambda now.
Yeah.
I mean, it just changes the x-axis, right?
Yeah.
The scale. You just so it's just a scale parameter. That's what I'm asking you to sort of say. And the other thing is very simple, also intuitively, right? I'm saying if the number of seats in the bus is really big, then nobody waits, right? Because it's like an infinite capacity bus, basically, right? Me. So it's not meant to be tricky, but so yeah.
That one?
Yeah.
Are you supposed to like explain all the parameters or just choose one and explain?
So I mean, I will see what you guys write, but what I meant is you hold one parameter constant and change the other 2, right? And then you do this for all 3, right?
Okay.
So I mean, I'm not like going to. It's just one point. I just want to understand how you guys sort of are parsing my question in English, and so I can kind of, you know, decide if I really want to have questions like this. I don't know. We'll see. But I do want to read it. Sorry, the autograder is taking longer, but I'll really do my best to it. Because what I want to do is give really specific feedback, and it's not for the handwritten parts, you know, the summary part. So I'll get it going soon. Okay, so where are we?
But is it possible to maybe some clarification about that next week on the seed and the lambda and the seeds? Is it possible to do that?
You mean like tell you the solution?
Short,
I usually will give you...
Explain how they are working.
Sure.
The right answer.
So I'll give you also a solution, right? Like I did for the first one, like a generic solution. There I'll sort of explain more.
Yeah, perfect.
So I don't know. Let me see. So I think we are online. I'm not really sure. I don't really care. If you're not here, you know, I can't do much about it. So anyway, let's continue with 10. Right. So the question was, how do you do R, right? Well, this is it, %R. You are an R shell. You're now launched R kernel, so you can do all the stuff in R inside this cell. And then you can also go, I don't want to get too much into R, and my R is rusty. This is how you do assignments in R. Or how do I do this? Yeah, so this is how so I'm assigning the variable 1 to R. So this is pure R. I don't want to bring R into this class, but I'm telling you that Sage includes R. So I think I can do B assigned A times A right? And then display B, let's see. Yeah, okay, this was a bad example. Okay, so it's there, you know. All right, let's go here. This is very important, okay? So we want to, remember I told you the justification for the maximum likelihood estimator is that it's actually asymptotically consistent. That means as the sample size n goes to infinity, and if the model were true, then the maximum likelihood estimate you know, will get closer and closer to it. And because the maximum likelihood estimator, right, the random variable, is actually, it changes with the data, right? So if you have a different realization of n samples, you get a different value. So there's actually a distribution on it. So we need to now understand how theta sub n hat, right? So this is our, so as the sample size n goes from 1 to and so on, right? We want to know what happens to capital theta hat sub n. This is the maximum likelihood capital E for estimator. This is the random stuff, right? This guy eats the data, right? So it takes all of the data and outputs a value in the parameter space, right? So then the question is, so we just, instead of putting all the x's, we simplify, we only call it theta sub n hat. So the question is, what is the distribution of this? So in other words, what is happening to theta hat 1, theta hat 2, as the sample size increases, as n goes to infinity? So this means now we need notions of convergence of random variables. Random variables. And limits, before that we need, you know, have some, so we talk about limits of random variables. Okay, and you guys all know about limits of deterministic numbers, I mean normal standard numbers, right? This is all you guys know. And I told you earlier we can think of a deterministic number like, say, I don't know, 4, as actually this point mass distribution, right? Which is all the weight, all the point mass at 4. So it's kind of a strange way to think about a number, but that's a natural way. So what we now saying is the parameter that we don't know, the hidden true parameter that's giving rise to the data is some number, let's say in 1 dimension, okay? And then the question is, what is going on with this random variable, right? So maybe theta sub n hat has a distribution like that, right? Kind of like normal. And as n increases, maybe this distribution gets concentrated more and more like this. You see? So that's all we're going to do. And that's basically, and the central limit theorem just says that that distribution function has normal shape, is normally distributed for a large n, okay? So here are the topics: limits of sequences of real numbers, limits of functions, limits of sequences of random variables, and then we'll get into convergence and distribution, convergence and probability, and then some basic limit laws and statistics. These are the weak law of large numbers and the central limit theorem. And then all of this buildup is just to understand in some intuitive way about this asymptotic normality of the maximum likelihood estimator. What do I mean by that? I just meant exactly this picture. So I told you this is the distribution function of theta hat, right? So then the question is, as n gets large, right, how is the distribution function of theta hat behaving, right? So asymptotic, again, is when n goes to infinity. When n goes to infinity. Normal, which is normal random variable. So asymptotic normality of maximum likelihood estimator is what we need to be able to do hypothesis testing and confidence intervals. So I kind of want to make sure that this is not like some black box for you guys. But we won't go too deep, right? It's not a math class. So So all of this mainly we need for set estimations and using the maximum likelihood estimates and parametric hypothesis testing. Okay. So this is kind of the big picture. We have parametric and non-parametric, and we're in the parametric world because the parameter space is finite dimensional. And then it's broken down into point estimation and set estimation. So this is what we just saw, MLE of finitely many parameters. What we're about to see is confidence intervals via the central limit theorem. Yeah?
Using your picture for this.
Sorry?
The picture you just drew. Can you just bring
It's all described. I just said asymptotic normality of MLE. Don't worry about it. So, because we're going to go here, so. So this is just recall on limits. So, oh, maybe I should, sorry about this. So, yeah. So I was going to do some Markov chains, but I skipped all this, so don't worry about this. Yeah. Okay, so the idea is this. So we talked about maximum likelihood estimation, and we saw the likelihood function change like this as n increased, right? So, you know, with enough points, this will be normally distributed. So now we're going to understand this, why this is happening, and how this makes sense. Because the problem with convergence of random variables is because they're random, it's not easy to talk about what it means to converge, right? So let's start with some very simple setup here. So I'm just evaluating some of the functions from before, and this is the secret data, and this is what we did last time. So this is now the extra thing. So what I'm now doing is, for any n, I'm not just doing one trial, but I'm doing 10 trials or something. So these are the maximum likelihood estimates. In this case, it's just the sample means. Okay? And so the question is, if I did millions of these, what will be the concentration, the density at a slice, right? So, you know, the question, and then the idea is that this is going to be normally distributed, and this normal distribution is going to get spike here and spike here. And the spike is going to concentrate on the true hidden theta, right? Theta star, which is 0.3. It's the connection with the last notebook. So what we notice is how the different lines converge on the sample, and to properly understand this. So there was a U-try where you're supposed to basically do exactly the same thing for the standard Cauchy, right? And I think I have all the cells, but just in case. So this is the Bernoulli running means, which is the maximum likelihood estimates over multiple independent trials for every sample size. But this is the standard Cauchy's running mean. Okay. See, this guy will never settle down, right? I told you this is Dartmouth's lightsaber construction, right? Because its expectation event doesn't exist. So every so often you'll get another big spike and it'll go somewhere else, and so it'll never settle down. So just to show you, this guy violates, the Cauchy guy violates the conditions for the central limit theorem. Yeah, I think it should be here. Oh, there it is, sorry. Okay, so if I try again, I mean, there's quite a lot of samples, and when we do doing 5 iterations, right? You see there's different realizations now. This guy's going all over the place, so it'll never stabilize. Yeah, so I was a bit ambitious, you know, and we just spent so much time on fixing laptops. So I was going to do Markov chains because it'll be a little more interesting, but yeah, don't worry about it. So let's just recall basics, right? So this may be too boring for some of you, so you can sort of fall asleep, but the limits of a sequence of real numbers. What do we mean by a limit of a sequence of real numbers? say little x1, little x2, little x3, dot, 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 which we write this way, right? X sub I goes from 1 to infinity, is said to converge to a limit a real number little a, and we say this, right? This is just recalculus. So we say that thing happens. What we mean by that is that if for every natural number m, a natural number n sub m exists such that for every j bigger than nm, xj minus a absolute value less than or equal to 1 over m. All this means in English is, if you're telling me the limit of xi is a, then for every m I give you, you have to give me an n sub m that depends on m, such that for every value of I bigger than that n sub m, right? You know, so if you go far enough, then the difference between a and that sequence, after you've gone far enough, is going to be less than 1 over m. So you can squeeze it as tightly as you want, that's all, into the future. Okay? I mean, that's the formal definition of a limit, right? So you guys do this in high school? No? Okay. Well, it's not a, yeah, you just gotta, you just keep going, right? That's all, right? So you just, so now we have to generalize this idea to random variables, because now each little xi is not a little xi. Each little xi is a capital Xi, right? It can take different realizations. Yeah. So how do you do this? That's mainly the question. So I mean, if you haven't done this in high school, I've put a lot of examples here. So this is the simplest example. If xi is 17, 17, 17, 17 forever, it's clear that limit as xi is 17, right? Because for every m you give me, I can take my response to you. So you give me 500. I'll say 1. That's my response to you always. Because no matter what it is, it's 17, so I'll always win, right? So you can think like that. It gets a little more interesting, you know, so just walking through the definition. So, and then this is a little more interesting, right? So if xi is 1 over 1, 1 over 2, 1 over 3, okay? So in general, xi is 1 over I. Then the limit of I goes to infinity of xi is 0, is the claim, right? Because I'm dividing 1 by bigger and bigger integers. So I'm saying the limit is 0. For that, what is the argument? For every natural number m you give me, I'm going to take n sub m to be equal to m itself, okay? So then for all j bigger than this m, xj minus 0 is going to be less than or equal to 1 over m. Done. It's a little more, okay, going on than the 17. Hotel California at 17, right? So you can kind of start doing more, right? This is supposed to be pre-calculus or whatever, right? So x sub I is 1 over p, 1 over 2 to the p, 1 over 3 to the p with p more than 0. So these are basic things you should have seen, I think. So then the limit is 0 again, provided p is more than 0, right? And you can make these nm arguments here as well. Some more. So anyway, we can do the plots. So variable IP, 1 over I to the p for the last example, and then see that it is kind of going down. And yeah, this is just for another plot. So if you want to build some intuitions, you can do this. This one's going to 1. This is the deterministic sequence, and so on. Okay. There is actually stuff you can directly do if you, once you have symbolic expressions, you can use dot limits and things like this, but I won't go into all of that here. So here's limits of functions. This is the next concept. So all we've seen is limits of sequences, right, downstairs. So now we're going to move to limits of functions of those sequences in the domain, right? So we talked about xi's converging to a. What's happening to some function of x now as an xi is converging to a? Right? So what's happening in the image of the corresponding limiting sequence in the domain? All right, so here's my yeah. So now we've been just talking about x1, x2, and then this boom, so something's happening at A, right? It's converging on A. Let's say there's some function, right, f of x. So now the question is, I'm interested in boom, chuck. So this will be f of x1, and boom, boom, this is f of x2, and so on, right? And let's say somewhere here, f of a. So the question is, I have a corresponding image sequence, right? So as this is converging to A, right, its limit, what is happening upstairs is the next idea. So these are called limits of functions, right? So you've seen this as well. You have to have seen this is how you start to define what is a continuous function. So we say a function f of x is going from the reals to the reals, has a limit capital L in the reals as x approaches A if this happens. So we say limit as x goes to A of f of x equals capital L. Okay? So this statement is true provided f of x is arbitrarily close to L for all values of x that are sufficiently close but not equal to A. Okay? So as I get closer and closer to A, I worry about what happens when it's exactly A. So this is slightly more subtle, right? So consider this function, f of x is 1 plus x to the power of 1 over x. Right? This is so here the limit as x goes to 0 of f of x is just this. So I'm interested in what's happening when I take any limiting sequence, right? Any x1, x2, whose limit is 0. Because I don't even specify which one it is, right? It can be any sequence downstairs whose limit is 0. Now what's going to happen upstairs in the F world? Oh, you just put in the value. And this is actually the E, right? This is, well, I don't know, 16th, 15th century mathematics, 16th, I don't know. So this is a pretty delicate thing in some sense. So this is the crucial point, right? So even though f of 0 is 1 plus 0 to the power of 1 over 0, right? 1 over 0 is undefined, right? You cannot divide by 0 formally in the reals, right? So this is, but still the limit exists in the image, and this is our E exponential. So x is defined as a symbolic variable by default, so we don't have to say var x unless we overwrote x in our kernel before. So we can say f is 1 plus x to the power of 1 over x. And you can do this type of stuff. So you can do, if I substitute x equals 0, you already saw the substitute command. Value error. What am I doing? Oh, that one. So yeah. So so if you directly substitute x equals 0 in the expression, then it's going to go crazy, right? Because it's going to say 1 plus 0 to the power of 1 over 0, and it'll say, I can't do this. I have a division by 0 error. This is coming from the power evaluate method, right? So then what we want to do is, if you want to divide by 0, I mean, it's possible. And Uppsala is one of the biggest reasons I came to the math department in Uppsala. We have some of the world's leading experts on this kind of mathematics, right? It's a very beautiful style of mathematics, and I really like it. It's actually Professor Warwick Tucker. He's the head of department. He gave a talk at Cornell when I was a grad student called The Art of Dividing by Zero, and I was totally sold. I mean, as a grad student, you know, at Cornell, like, seminars have free food. So I just was a single guy on a motorcycle, so I just hit the seminars and ate. So anyway, I just went to all the seminars pretty much. And so this is important, right? Why is this important? This kind of mathematics, like 1 minute excursion, is essentially the mathematics that is doable mathematics in some sense. So you have to actually do the mathematics, do all of the formal mathematics such that it conforms to the engineering confines of the machines, right? The floating point processor, the sensors, and stuff like this. And where is a concrete application of this, in sort of non-militaristic application of this? So these are these probes. Remember these deep space probes that the Aussies sent and EU sent? So these probes are essentially like the next Viking ships, right, or whatever. all over the world. India is pumping satellites for free, right? So these ships are now doing gravitational sailing. They're not sailing the waters like the ships built with, with sails, right? They're sailing gravity, right? What I mean by sailing gravity is they have to use very little energy because they're going deep space, but then they have to be very careful about exploiting the planetary motion. It's a many-body problem, right? So they have to go to the right place at the right time and give the right kick, and they go really far, right? It's like slingshotting. And to do this operation in a robust way, you need to account for all the errors that come from your machine sensors, right? You'll have sensors to measure certain, I don't know, gravitational fields, and all these things will be set valued, right? You won't know it exactly, right? So then all your OD, whatever, all these various control algorithms will actually have to formally propagate all this uncertainty. So when you take a decision, the decision means you instruct the machine to give the right pulse, the kick or whatever. It has to be done in a more delicate way. And it's kind of the same problem when sort of, I don't know, Japanese near-Earth asteroid mining robots are sent, instead of getting the ore from Australia. So they just go near asteroid mining. This is a robotic swarm that lands, right, and mines stuff, right? This gets more complicated, right? Currently, we don't have international law to checkmate, and if the Japanese robots are conforming to their own engineering standards, because in the worst case scenario, right, you could have a near-Earth extinction event if the engineering is wrong and the maths is wrong. You see what I mean? You can send a big thing back to Earth and just like boom, dinosaurs. So it's not just dividing by zero is necessary sometimes, and then enforcing others who are not doing division by zero correctly according to their own standards is even more important for international law. I'm just saying these things because you're STS students. Right? All right, good. So you can get some idea of what is going on with the two plots on different scales, right? Yeah. So maybe this is kind of boring. So let's get into random variables. Okay, so that's just a recall on limits, right? So now the limits of sequences of random variables. So I told you we can think of deterministic numbers as point mass. So this is the mass function, and this is the distribution function of just. So these are, you can think of them as point mass random variables, deterministic ones as. Okay. So this guy is at 2, and this guy is at 2 as well. So so you can, I wrote this in the first week or something. So you can think of this as 0 if x is not theta, and 1 if x is theta. So this is a point mass theta random variable. So now for every theta that is a real number, I have a way of talking about that real number as a random variable. So what we saw before, the standard sequence in the reals, is now applicable to only this particular random variable. And so if you had a sequence of random variables xi with point mass at theta I, but then now I is 1, 2, 3, then we could talk about a limiting random variable x as a point mass theta random variable. Yeah. So yeah, this is the way you can kind of relate it back to the limits, right? So this picture is sort of making this kind of leap, right? So remember, I just put these dots. These x's are x1, x2, or x1, x2, boom, 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 converting to this red dot, the limit a. Now I just turn them into mass functions. That's all. Nothing. So we're back to deterministic setting, but now from a probabilistic view. So we want to generalize this notion to a limit of other random variables, not necessarily point mass. That's the game, right? So let's first of all recall this most elementary random variable called the Gaussian or normal random variable, right? So how do you guys call this in Swedish? Gaussian or normal?
Normal fördelning.
Okay.
But when we talk about it, we also talk about Gauss-kurvan.
Oh, Gauss-kurvan. Okay, that's cool. Yeah, it's by Gauss. Yeah. Yeah, good. Yeah, yeah. What I'm calling the bell-shaped curve is your Gauss-kurvan, I think.
Maybe not. Normalfördelningskurvan.
Well, it kind of doesn't matter, right? This is the beauty of mathematics. So it's just e to the minus 1 over 2 sigma squared x minus mu the whole squared divided by sigma squared root of 2 pi, right? So and I'm not like sort of blabbering, right? So you can just make sense of this. So what is this? You know x squared, right? X squared. X minus mu is a translation operation. Right? So you just move it around. And then this negative sign, remember it flips it. So boom, 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 flip. So then you just do this 2 sigma squared, it scales it, right? It's a multiplication operation. It's squares it. And then of course that's downstairs, so you exponentiate it, right? So it brings it above the 0. And this is a rescaling so that it comes to 1. So it's not a... so you're smiling, I'm Indian, I just sort of move. So it's not a... Yeah, I don't know. Yeah. Yeah, so this is what we're going to build up to, right? So this is normal. You can play around, right? This is what I was trying to do. So you can change mu, it moves around, move it to 10, and sigma is just going to be, so that's called the location parameter, because it just moves the location, you see. It just moves it around. Wherever you want it, it goes there. This is called the scale parameter, because if we increase this, you see how it's changing the scale? So it's actually called locations. It's location and scale, right? So if I decrease the scale, see it's concentrating, and then I can do 0.001. Oops, that's too far. 0.1. Yeah. So when I concentrate it like that, you see it's spiking because I'm decreasing the variance, right? So this is scale and that's location. So usually it's like this, right? So it's centered at 0 and the standard deviation is 1. So this is called the standard normal. Okay. So now this is our problem, right? We want to consider the sequence of random variables, capital X1, capital X2, capital X3, dot, 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 where each xi is normal 0, 1 over I. Okay? So you guys saw this sequence, right? 1 over 1, 1 over 2, 1 over 3, early on, goes to 0. So the variance parameter is getting smaller and smaller in this xi sequence. The location is just at 0. So the question is, how do we talk about this guy, right? So is this getting, as this concentrates like that, what's going on, right? Oh, so I don't know, that's the question. How do we talk about this stuff? So here's the sort of animation of this. So the first sort of guess is like, okay, this guy is going to 0, 1 over I, the variance. So maybe it's just, the limit is just the point mass random variable at 0. No? I mean, it's a good guess, right? Because everything is concentrating at 0, so why not? But no, but there's a problem, right? Because for any I, however large probability of xi equals 0, what is the probability that the xi random variable is exactly 0? This is going to be always 0 because xi is a continuous random variable, right? No matter how small the variance is, it'll be greater than 0. And the density is continuous, so it will never put any mass at one point, right? It's for continuous random variable. So this kind of is busted. This reasoning won't work. Direct reasoning won't work. So we need to refine our notion of convergence when we're dealing with random variables. So the first notion of convergence for random variables, the easiest one, or the simplest one, is called convergence in distribution. This is the distribution function sense. So what we mean is let x1, x2, dot, dot, dot be a sequence of random variables and let x be another random variable. Then we say we let f sub I denote the distribution function, or CDF, cumulative distribution function of xi. And then we let capital F denote the distribution function of x, the limiting random variable. Then this is the definition. Now, if for any real number t, okay, at which capital F is continuous, right, the right-hand side. So capital F, the distribution function of the limiting random variable, should be continuous at t. So for any t at which capital F is continuous, then we have this limit happening. The limit as I goes to infinity of f sub I of t is going to converge to f of t for every t. For continuity goals. That's it. And these are real limits, right? This limit is just a limit of real numbers because f sub I of t is a real number, right? It's the value taken by the distribution function. So there's nothing magical here. That's the classical deterministic limit. So that's basically convergence and distribution. So there are many ways of writing this. So if this happens, we say convergence and distribution, and then you put x sub I arrow and then put a d on top of it and say it goes to x. So that's just shorthand for xi converges to x in distribution. Okay. But you guys should not forget the probability under the hood, right? So there's little omegas and capital omegas and events and probabilities. So what actually this means is saying that for any t in reals, this limit, as I goes to infinity of fi of t equals ft, is equivalent to saying that for any t where this continuity condition is met, the limit as I goes to infinity of the probability of the set of all omega such that each xi of omega, right? Think about it. We did random variables mapped from omegas to the real line in this case. But then for every I, there is this mapping, right? So we're now looking at the set of all omega such that xi of omega is less than or equal to t. And the probability of that set is equal in limit to the probability of the limiting random variables set, right? Set of all omega, x of omega less than or equal to t. So that's what it really means axiomatically. So of course, depending on your experiment, you may have to kind of think about this in depth, right? But not for the exam, right? The exam, you just sort of, do something similar to the sample exam. So, okay. So now, armed with all of this, we can go back to our sequence of normal random variables, where xi is, the xi sequence is 0, 1 over I, and let x equals the point mass at 0, right? And now we can say that xi converges in distribution to the x, to the point mass random variable at 0, right? Because we have no problems now, right? Because you see, the earlier problem was this. So I'm going to do in green the point mass random variable, pluck it out, and put a 1, right? So this is 0. So this is my capital F for the point mass random variable. So now that's my limit. So now what I'm saying is the following. The x1 is standard normal, so it'll be something like, it's going to go through half, right? It's not the best picture, but this is the CDF of, so this is f sub 1, right? Of x1, which is normal 0, 1, right? And what is the next one, x2? x2's distribution function is f2, right? So I should say distribution function of, so this is distributed as whatever. So this is normal 0, 1 over 2, right? So this guy is the second guy distribution also going through half, symmetric. So, but then it's going to be spikier, right? So it's going to go faster. I mean, I'm not drawing it properly, but you get the idea. And of course, I keep going like forever. It's going to just start hugging this point mass guy like crazy, right? More and more and more, right? That's the picture. But the beauty is this is fine. We can now say xi converges in distribution to point mass of 0, 0. This is okay now because we've changed the definition. We say convergence in distribution means for every t, so I'm going to call this t, or we can call it little x, t. So for every t at which capital F is continuous, right? The fi's should get arbitrarily close. So we've basically defined it so that we avoid this point. Because at the point 0, the distribution function is not continuous, right? It jumps. So we can ignore that. But everywhere else, like anywhere we look, this will eventually get close to 1. And anywhere to the left of 0 we look, this will eventually get close to 0. You know, that's all it is. So that's kind of how you solve a problem in math, right? You just define it so that it's a definable one. It's not a lot really going on. So that's just convergence and distribution. So I'm just showing you the PDF now. So we looked at the distribution function, but we can also say, if it converges on distribution, let's look at the PDF of this sequence of random variables. Okay, so that's basically, yeah. So convergence and probability is slightly different, right? So, so this notion is where we say, this is the definition. So we say a sequence of random variables x1, x2, dot, 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 converges to a random variable x. If for any real number epsilon, that's greater than 0, the limit as I goes to infinity of the probability that xi minus x is more than epsilon is 0. So that means, this means what? This means it's the set of all omegas where xi and x differ in absolute value by more than epsilon, where they actually differ by more than epsilon. That set, the probability of that set is actually just 0. So this is another notion of convergence. And then you put a capital P over here. So I just want you to know that there are many notions of convergence. So this one's is an interesting and subtle one. Okay. So the main thing is to note that convergence and distribution is implied by convergence and probability. So it means if a sequence of random variables converges in probability, it automatically converges in distribution. Right? So then convergence distribution is the weakest form of convergence. Yeah. Anyway, so here's another quick interact. There we go. So this brings us to these things you have seen already in Swedish. So we're sort of doing it in English now. Just mostly all recall. So we have, when we look at this sequence of normal random variables, and if x is 0.0, we can also show, I'm not doing it in detail, but you can also show that xi converges in probability to x. Okay, with a little more work, you can do this. The formal proof, you learned this in a math course in first year math course in probability. Intuition behind law of large numbers and central limit theorem is what you want. So the weak law of large numbers is the following. So it basically says that if I have IID samples, x1, x2, dot, 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 they're all independent and identically distributed as x1, say, or any one of them. They're all the same distribution. And if the expectation exists, then we say the sample mean converges in probability to the expectation. Right? So this is the weak law of large numbers, and I will recall this. We won't get too far into this. So please look at this on your own. This is just the central limit theorem. I'll just mostly state it. So then we're basically ready to do confidence intervals next time. Okay. And hypothesis testing. So I think someone has a new machine that they need to, but can you not figure out how to do this on your own, because you've already done it on your own machine, right? Because the TA is sort of paid to do this, right? And there are some videos and stuff. Because I have a meeting with faculty to make sure that the exam for the course satisfies the retake students as well. Yeah. So I can't.
It's just like this message that it couldn't connect.
Just bring your machine. Let me unpack, and then I'll sort of start you off. Okay.